the black dots and the red dots, does anyone have any ideas which one is more correlated with the x's? Go ahead.
The black.
Pardon me?
The black.
Now, why did you say that, Robin?
Because they're so close together.
That's right, that's right. Like, look at how tightly they're, how close they are together, and whereas the red dots are really dispersed. So, I've listed, I got cut into the previous page, but correlation can be said to reflect strength of association in the presence of noise. Now,
Well, you just said that the scale does not matter, right? Could that be just? Could that be the red is just a scale version of the black? And could they actually have the same correlation?
could they have the same correlation? Well, let's.
Right? If you take a number, take something. If you multiply by something, can I make them this big? And
Well, okay. Well, why don't we take a quick look at the formula? So remember, it was covariance over standard deviations. So under the argument you just gave me, you said one might be a scaled version of the other one. So then you would say, oh, the correlation should be 1.
no, the correlation should be the same. I didn't say correlation is one.
So sorry.
No, I mean these red dots
Right.
is sort of
Got it.
a
The
scale
correlation
version
should be
of
the
the
same.
black word.
Got it. Okay. All right. So let's consider the correlation of the red dots. Okay. You say that they're a scaled version of the black dots. So in that case, do you agree that the red dots have the same y mean, or have the same mean as the black dots? Are you willing to accept that?
I see a point.
Okay. So do we have to go through this? Did you understand where I'm going to go here?
Yes.
Is the standard deviation is not the same, so the correlation will be smaller.
Okay.
Got it?
Got it.
Okay.
Got it.
So if they didn't have the same mean, then that argument might not.
That's right, and we'll see a couple cases like that in the next set of misintuitions. But
I see.
the green dots are very similar to the blue and green dots are very similar to the red and black dots. Only the correlation there is negative. So if you wanted to fill in the blank here, it turns out that the black dots have correlation 0.9, and the red dots have correlation 0.5.
No, it's actually
Yes.
much. Let me describe. It's much harder by looking at a picture to figure out roughly where the number is.
Right. That's
To
true.
rank them is easy.
Good point. Good point.
That's
yes.
very hard.
Yes.
You can easily misled by the graph.
You raise a good point. It's hard to tell what correlation is, but it is very useful on a relative level when you compare two sets of associations. Okay, now let's move down to the next graph. Well, thank you.
We're obviously going to run a little bit over a bad time management, but
Okay, now let's look at the next set of dots. Now, take a minute to just drink these in. And when you're ready, does anybody have any idea whether the black dots or the red dot will have higher correlation?
so,
Which two colors, sorry?
Black and red. Black and red.
I think they have the same correlation.
Why do you say that, though? Because
You told us it's a strength of linear relationship,
Right.
right?
right.
And it doesn't really matter how I turn this thing, does it?
That's correct. That's correct. Yes, but
No, but wait a minute. But if I turn it this way, it'll become flat.
well now you've raised a special case. Now, when you talk about turning things,
Yeah.
you also have to talk about changing the variance as well, because like you just discussed, if the variance is changing, then or if the variance is the same, then of course the correlation. Hold on, let me
Wait,
just
but
scratch all
zero
that.
there
Go
will be
ahead.
0, wouldn't it?
Pardon me?
But if I put like one line
Right.
on 0, it will be 0, isn't it?
Yeah, it turns out that once you hit 0, then it will be 0. But
Wait, what will be 0 when you hit 0?
well, Charlie was talking about twisting the set.
Well, I was thinking
points.
about intuitively when I was going to twist this thing, right? It shouldn't change the correlation, right?
Still in.
But the moment I hit horizontal,
The moment
then
you
the
hit-
correlation becomes 0, is it?
Yeah.
So does that mean you get closer to 0 correlation as you get closer to horizontal?
No,
No,
it's a sort of
it
sudden,
doesn't.
is it?
It doesn't. Right. It's
Is
So
it
it's not like it
interesting?
just jumps to
Yeah,
0?
because then it goes to the other -1, right? Something weird. This measure has a problem then. Don't you think it's
Well, yes, it does. Yes. So now it turns out that, so if looking at the red dots and the black dots, Shelley is right. They do, in fact, have the same correlation. But now that would fool a lot of people, because a lot of people would look at this and say, hey, wait a minute. Like
black is more, right?
Yeah, black is more, right? Okay, so there's an important blank there for you to fill in, which is correlation is not slope. Okay?
That was the one.
Yeah,
he tried to confuse me.
That's true, yes.
Wait a minute, but we said the correlation.
No, it's distributed, but it's not. You didn't say that it's equal, since you multiply it by.
Okay.
Now, let's
You asked about the distribution.
the next thing I want to compare here before we're done is what about the black dots and the green dots? Any ideas on those?
That's exactly the same, is it? It's just moving down.
Turns it is, right. But does moving things up or down change the correlation?
No,
That's right. And why is that?
since you scale it by y and
There
by
you go.
x.
Yes, that's exactly
Scale it
right.
This doesn't work. This doesn't change.
Right.
This doesn't change until
Right.
it changes.
So in the next blank, the next blank on page 3, you can write correlation is not an intercept. Okay?
Okay.
Yes. And the blue dots were also another shifted slope. They weren't anything out of the ordinary.
And what's the third line you want to put in? The intercept and the slope does not matter?
Well, I was going to say the scale and the location.
Oh, the
don't
scale.
matter. Right. Yes. Okay. And now, well, here's another potential misintuition with correlation. Is correlation transitive? And what that means is, if x is correlated to y, and y is correlated to z, then is x correlated to z?
Has to be, right?
Roy, what do you think?
Probably.
Probably. Yeah.
That's a smart answer.
Probably, right. There you go. With what power?
With high probability.
That's true. That's true. Well, it's actually an interesting result, but no, that doesn't mean that x and z are necessarily correlated. Pardon me?
I was just drawing a little picture in my head.
Yeah, it's kind of hard if you think too much about the pictures in this case, because what you have is multiple dimensions going on here. We'd have to draw a 3D plot to really see what was going on. But I think it works better just to think of some examples.
Yeah.
Yeah, that's what I was doing.
No, actually,
Yeah.
there is a very easy
Mhm.
example to show. Correlation is the cosine of the two. If you think
Okay.
about H as a vector, so it's easy to have, one cosine is like that, the other cosine is like that, but between them is more than
Oh, really?
95.
Or you can
Okay.
both one in each direction.
Right. I mean,
One in each direction, then it can become 0.
yeah. I mean, so it's all sorts of possible. Right?
Right. Okay. Oh, okay. I guess that there
It's a
was.
good example.
Thank you. Yes. And I think you can also think of the example, say, of baseball, which is that home runs are correlated with base hits correlated with batting average. But it turns out that home runner hitters don't tend to have high batting averages, and that's kind of interesting. And being as a more facetious example,
That's interesting.
being me is correlated with living in Hawaii. Living in Hawaii is correlated with having a tan. Yeah, is not correlated with having a tan. There we go. And as a I know we're running out of time here, but maybe you can go back home and think about this. But in these next set of examples are pretty famous. For example, it's called Anscombe's correlations. And it turns out that which of these do you think has the highest correlation with its y, comma x?
Green ones.
The green ones?
No, the black ones.
The black ones? Okay, so now we have a couple of opinions on the table. Roy, what do you think?
Oh, I can see that one.
Oh. No, I saw
I
that.
bet it's
No,
the same.
actually,
The blue.
actually probably the blue. And I didn't see the other dots.
Yeah.
That's right.
The blue ones.
Blue.
Okay. Well, I think the one who got it right was Casey, because it turns out that these are all exactly the same correlation,
Yeah.
of 0.81. And well, it's kind of interesting because let's go through and try to interpret these quickly. The first thing is your standard set of points you would think of as, it's y is related to x, but with a little noise. That's sort of what we want for correlation. That's the ideal case. Now the next case is sort of what Shelley was talking about earlier, which was a nonlinear relationship, but it still has a linear component. So that correlation is still positive, yet there's clearly some other nonlinear pattern here. For instance, this could be Roy's test scores. He was doing well, and then he came to Harvard, and boom.
Oh, nice.
That's right.
Well, you're insulting the student in the class. This is like a.
That's right. And then we have the next set here in green, and these look extremely linear, so you would think their correlation is like 1. But there's that one screwy little point screwing up the correlation. So it turns out that drops the correlation from 1 to 0.81. And in the final set, we have things that are definitely not correlated, except for one screwy point, which happens to be in the right direction. And because of that one point, the correlation is 0.81. So you would think that these are very related.
So that's a great example of these we call a leverage point, because it has a leverage point.
Yes.
All right, we exactly 107, so we have exact 2 hours. Thank you very much. And thanks to everyone. I don't think we have time to discuss about it.